I want to find, so here's the sentence, right? The volume of the solid obtained by rotating blah, 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 blah. It's obtained by rotating the region bounded by what do I got here? Sure. X equal to 6y squared, y equal to 2, and x equal to 0. About the y-axis. So first around the y-axis. I think that actually they're all around the y-axis. So it can be computed using the method of disks via an integral. So we've got disks, and we want to find the integral from a to b of what goes in here, d what. Right, that's kind of the setup for the question. So basically, the problem is trying to lay out for you. Set up the integral, right? Tell me what a and b are. Tell me what you're integrating with respect to, so on and so forth. So let's draw the picture. So first and foremost, well, let's see, we've got x equal to 6y squared. We've got, what do we got here? Y equal to 2, x equal to 0. Okay, so x equal to 0 is just the vertical line here. X equal to 6, well, let's see, y equal to 2 is this horizontal line. And x equal to 6y squared is going to be, well, what does x equal to 6y squared look like?
A sideways parabola.
Right, specifically rightward opening. So it's going to look kind of like this. So the region we're looking at is this region right here. This point of intersection, well, we know that x is 0 and y is 2, so it's the point 0, 2. That's just the origin. And this point here, it's where y equals 2 and x equals 6y squared intersect. Well, that's easy enough to find. If y equals 2, x is going to be 6 times y squared. So x is going to be 24, which is 6 times 2 squared. Mm-hmm. Okay, so now we want to use, so we're going around the y-axis. So I want everybody to type in the chat D or an H, D for vertical, H for horizontal. If we're going around the y-axis and we want to use the disk method, right, that's what the first problem is asking for, are we going to use a vertical strip or are we going to have to use a horizontal strip? Let me know in the chat, which is it? Am I using a vertical strip to use the disk method, or I'm using a horizontal strip to use the disk method? Right, it's a horizontal strip because the disk or washer method requires a strip that is perpendicular to our axis of rotation. So horizontal strip automatically means we're using which variable, X or Y? Also in the chat. Chat it up. Awesome, yes, right. Horizontal means Y. Great, which is awesome because we already got things in terms of Y, right? We have X as a function of Y. We have, well, yeah, X as a function of Y. So if I want to do this one, so I like to draw the disk. You don't have to really draw the disk. You can just say the volume of the disk. We know it's going to be pi times the radius of the disk squared times dy. We know it's dy because you guys all just told me we're using y. Okay, so then we actually have to figure out what things are. So the radius is just how long the strip is. Well, the length of that strip, well, I take that back. That's not quite the right thing to say. The radius in the disk method is how long the strip is. The radius in the washer method is more how far the function is from the axis of rotation. It's just in the disk method, one of your boundaries is the axis of rotation. So you don't have some inner thing you're taking out. So the disk method is how far this outer function is from the axis of rotation, which is just this minus this. So my volume of my disk here is pi times the radius, which is going to be 6y squared dy. And now to find the total volume, or to set it up, we're actually not going to find the volume, we're just going to set it up. The total volume would be the integral from, well, let's see, we're integrating this, and you do need to write the pi in it, so it's going to be pi times, we could simplify, we can write it as 36y to the 4th dy, and then my limits of integration are how far it's basically how far your strip can slide in the direction that it's not oriented. So this strip is oriented horizontally, how far can it move up and down vertically? Right, 0 to 2. Okay, now we're going to ask the same question, but doing it with cylindrical shells. So basically all the questions just asked, now the answers are going to be the opposite. Right, so if I want to use a shell, I have to use a vertical strip. In this case, because the vertical strip is parallel to the axis of rotation. And if I want to use a vertical strip, that means I have to use the x variable because vertical strip gives symmetry. So if we're using a vertical strip, then the volume of our shell is always 2 pi r h d whatever, in this case dx. The radius of our shell, so I always like to think of my vertical strip as being x away from the y-axis. Just like if I was doing the shell method using, like if I was doing this around the x-axis, in fact, I might do that anyway. Just like I would think of this being y away from the x-axis. So my radius here is x. And the height of my strip, or the length of my, or the height of my shell, right, is going to be the top function minus the bottom function. I have to find the functions as functions of x. So the top function is y equals 2, a constant function of x. The bottom function, well, if I solve for y here, 6y squared equals x, y squared equals x over 6, y equals plus or minus the square root of x over 6. Which is it? Is it the positive square root of x over 6 or is it the negative square root of x over 6? It's an excellent question.
It's the positive.
Right. And the way we know it's the positive, it could be the negative sometime, right? But the way we know it's the positive is literally we're saying y is positive. Well, look, we're above the x-axis. So yeah, y is positive. But if for some reason you're using this bottom part, that would be the negative part. So we get y equal to, was someone else something?
Yeah, I had a quick question, James. Could you explain once again how can we decide our the radius? For the
shell method?
Yeah, yes.
Sure. So the shell method typically, so let me say this general statement. If you're going around one of the normal axes of rotation, either the x or the y axis, in the shell method, the radius is just the variable that you're already using to integrate. So the radius literally is just going to be x. Now, if, for example, let's say instead, just to kind of change it up, if we were going around, say, the vertical axis, x equal to -1, then our radius would be, well, this is x to the right, but then I have another 1 more to the left. So my radius would be x minus -1, which would be x plus 1. Or if my axis of rotation was, say, like over here was like x equal to 27, then the radius of my shell, right, would be this distance here, which would be 27 minus x. But we have to get really comfortable with the idea that we are saying that this vertical strip is located at x, away from the y-axis. And then we're going to let x range between its limits of integration. X can be as small as 0, as big as 24.
Okay, yeah, that makes sense. Thank you, James.
But yeah, it's always kind of like the shell method, the radius is just x if you're going around, right, the y-axis, and it's just y if you're going around the x-axis. Yeah. The height of my shell is going to be the top function. We were finding the bottom function. So it's going to be 2 minus the positive square root of x over 6 dx. And then the actual integral would be the integral of all that, 2 pi x times 2 minus square root of x over 6 dx, from as far left as 0 to as far right as the rightmost x value, which is 24. And that's how you would set these up. Well, then they actually do want you to calculate one of them. So if I had to calculate one of these, either this one or this one, which one looks easier to deal with? The one with the x's or the one with the y's?
It'll be I believe the x.
I would actually have to disagree. I would actually say the y's, and here's why. The y's, you just have 36 pi times y to the 4th. There's one thing that anti-differentiate. Here, for the x's, you have a 2 pi x times 2 minus the square root of x over 6. So you have to distribute the x, integrate each of those, and you also have a square root, meaning when you do x times the square root of x over 6, you're going to get like x to the 3 halves and have to anti-differentiate that, which is just a little bit less nice. In my opinion, this one here is super straightforward. You're going to get 36 pi y to the 5th over 5 from 0 to 2, and then you're just going to get 36 pi times 32 fifths. That seems much faster than whatever I could have done over there. Are there other questions about what we've done here?
Yeah, James, is pretty much the only thing I'm just confused on is like the whole like when do we know when like that we have to use the shell method? When do we know that we have to use the disk method and stuff like that?
So the real answer is you never actually know. Okay. So you could, well, I mean, and the more real answer is you can technically, with some exceptions, you can almost always use either method. Mm-hmm. Sometimes there are reasons you can't, like the function doesn't integrate one way versus the other, or some other weird, or it's really hard to solve. Like for example, if I was given, so let's say we had this. Let's say I had the function, sure, y equals x cubed minus x. I'm just going to try to make this simple. Yeah. On the interval. So I want, come on, James. I want this. I want this region. So y equals x cubed minus x. Has intercepts at -1, 0, and 1. It looks kind of like this. And I want the region between this and y equals 3 and x equals 1 and x equals -1. So I want this region. And the point I'm trying to make with this region, so let's say I want to find the volume of this wonky looking solid or wonky looking region revolved around the line y equals -2. Okay. This one, there's only one good choice. What kind of strip do I really kind of have to use? These are H's. These are H's. Do I want to use a horizontal strip? Do I want to use a vertical strip? See one brave soul. Anybody else want to chime in? I'm not saying Eric is wrong. I'm just asking for more feedback. Two brave souls. Yeah, I definitely want to use a vertical strip. A horizontal strip is going to be terrible because right here, right, like in this whole, like, so, right, from here to here, it's super okay. But from down below, right, you have like this weird kind of thing where you have to do, and here's the real issue. Try solving that for X. I'll give you all day. I'll give you all year. I'll give you the rest of your life. You can't. So, or I mean, there's some really high level mathematics where you can kind of solve cubics, but it's really kind of bizarre. So the point is, right, if you can't solve for your other variable, right, if you can't solve for x as a function of y, you can't really use a horizontal strip. So here we'd have to use a vertical strip. And so then, knowing that we have to use a vertical strip, if we're being asked to go around this axis y equals -2, well, we have to use the washer method. So our volume of our washer is going to be pi times my big radius squared minus pi times my little radius squared times dx. Right? And I knew I had to use the washer because I was forced to use the vertical strip because of how the function is, and my axis of rotation is horizontal. So the perpendicular, so we use washer. So this would be pi, let's factor out the pi. The large radius is 3 minus -2. Which is 5. And my small radius is the function minus -2. So then the volume of this weird looking shape, which would be like kind of like a cylindrical shell, but some weird curvy part cut out of the middle, right? The volume would be pi times the integral from -1 to 1 of 25 minus this garbage, x cubed minus x plus 2 quantity squared. On the other hand, if someone said, James, instead, I want you to find the volume of the washer, sorry, not the volume, find the volume of the same solid revolved around the line, say like x equal to 2, well, I'm still stuck using a vertical strip. But now since my strip is parallel to my axis of rotation, I have to use the shell method. So if I'm going around x equal to 2, so then I'm looking at, I'm looking at my cylinder, which is going to be, sorry, this is kind of big. Right, it's like, whoa, there's my cylinder. I should say not a cylinder, a cylindrical shell. Right? And again, we think of this strip being located at x. So when I find the volume of my shell, which is 2 pi r h d x in this case, that's going to be 2 pi. The radius isn't x, but the difference between x and my axis of rotation, which is 2. Sorry, I know this x equals 1 is kind of like in the way here. Right? This distance here is 2 minus x. So it's 2 pi times my radius, 2 minus x, times my height, which is the top, minus the bottom, x cubed minus x, times the dx. And then the volume of this thing rotated around x equals 2 would be 2 pi times the integral, again from -1 to 1, of this mess here. 2 minus x times 3 minus x cubed minus x. So, very long answer to your question, but the idea basically is you can use whatever method you want unless they've specifically specified, which they did in this question. So if you use whatever method you want to pick the type of strip that works the best for the region you've got. And then depending on if your strip is parallel to your axis, great, you're using shell. If your strip is perpendicular to your axis, great, you're using washer or disk method. Mm-hmm. Whereas in this previous problem, they told us, okay, here's your region, use the shell method for rotating around this axis. Well, if I'm using the shell method, I have to use a vertical strip. If I'm using the disk method, I have to use a horizontal strip because my axis is vertical. So it's just pretty much whenever it's convenient for you. Right. Okay. Whenever's most convenient for me, unless they tell me how they want me to do it. Yeah, of course. Thank you so much, James. Of course. Yeah. That one looks interesting. Okay. Should we do more volume stuff or should we move on to arc length? You guys are like, or, well, yes. We can come back to volume if you guys want. If you have more volume questions, I'm happy to address them. But let's start taking a look at arc lengths. So the question I should really ask you guys is, how much do you want me to explain about arc length? I guess I should probably explain kind of the whole deal. It's not terrible, but we should talk about it a little bit. So the thing about arc length is, right, like normally we're used to integrating with respect to x, with respect to y, but let's say we have a particle moving along a curve. The arc length it travels, we'll call s. So let's say we've got some curve, and there's a particle that's moving along. So right, it's here, and then it's here, and then it's here. Right, so it's moving this way. And let's focus specifically on when it moves from like here to here. So this length it travels, s, is how far the particle travels. And so s is how far the particle travels. And the reason I mention this is because then we can think about what ds dt is. ds dt is the particle's velocity. Okay. Well, I would like to be able to calculate that. Well, if we zoom in on this, it kind of looks like, it looks pretty straight. I mean, and the shorter your interval, right? So this is very much like, right, you take the area under the curve, you break up into rectangles, and make the rectangles really thin so that the tops of them really aren't like that jagged. Same idea here. We're kind of zooming way in on this so that you get a really short segment that's essentially straight. And so when you do that, you can say, well, this is essentially straight. And we're going to say that, and this length here is, I'm going to call this a ds, because it's pretty small, right? It's a small change in s. What I'm going to do is I'm going to pretend like it's the hypotenuse of a triangle, where this part here is dx, and this part here is dy. So, right, dx dt is the velocity in the x direction. And similarly, dy dt is the velocity in the y direction. Well, then we can use the Pythagorean theorem and say, right, ds dt is the velocity in the direction we're actually going in, or just the velocity. We can say, you can either do this, you can say that ds squared equals dx squared plus dy squared, and then divide everything by dt squared. Or you can just say, ds dt squared equals dx dt squared plus dy dt squared. I kind of like doing it this way, because then we can take the square root of both sides, say ds is equal to the square root of dx squared plus dy squared. And then I'm going to divide, I'm really just going to multiply by 1. And say this is the square root of dx squared plus dy squared times, now watch this, dt over the square root of dt squared. Same thing, dt is positive. Just writing it this way, so that then when I put this over here, this is going to be the square root of dx squared plus dy squared over dt squared. Or the square root of dx dt squared plus dy. So a small change in s is equal to the square root of dx dt squared plus dy dt squared. And then if I want to find the total arc length, which I often call s, I think most books usually call it L, but the total arc length, we're just going to integrate all this, right? We're going to add up all the small pieces. So I'm going to add up this small ds and this small ds, and right? we're just adding them all up, which is what we do when you integrate. Okay, so the arc length, one formula for it, and this is actually the formula that we see last kind of, is the integral of the square root of dx dt squared plus dy dt squared dt from e to b. Now, you probably haven't seen this formula yet. That's okay. So here's what we're going to do now to kind of bring it back to what we actually want. We're going to say, well, let's say the curve is, let's say we've got some curve. It's given by what? So remember this one. Yeah. So let's see here. Yeah, we can do that. So let's say our curve is given by y equal to f of x, which is typical, right? So instead of using the parametric form, which is there, we can change this so we can have what we want. Here's what we're going to do. We're just going to say let x equal t, and then y is going to equal f of t. So then dx dt will be 1, and dy dt will be f prime of t. We're okay with that? Okay. So then our formula, I'm like, everyone okay? Great, let's go. Stop me if you have questions. Our formula will be the integral from a to b of the square root of dx dt squared plus dy dt squared dt. But that's just going to be the integral from a to b of the square root of, well, dx dt is 1 plus dy dt squared. But dy dt is really just the same as dy dx. It's just a different variable. So instead of using t's here, we typically just rewrite it using x's. So we're going to say that that's really just the integral from a to b of the square root of 1 plus dy dx, 1 squared dx. So that's your arc length formula. And technically there's two versions. There's actually technically three versions of it. There's this parametric version, which I imagine you guys haven't focused on. Correct me if I'm wrong. I don't think you've talked about this one yet. There's the parametric version. There's this version where y is a function of x. And then there's the other version where x is a function of y. But what I would really, really, really encourage everyone to do, because it's going to be helpful when we talk about surface area in the next section, is to think about this quantity that you're integrating. This thing here is just ds. This thing here is just ds. This thing here, including the thing at the end, is just ds. And the arc length is just the integral of ds. The reason I bring this up is because next section, when you talk about surface area, well, surface area of something rotated around is essentially going to be the circumference of the thing times the arc length. It's going to be 2 pi r times the same ds, whichever one it is. So that's how I would encourage you to think of it this way. All right, great. So there's how you get the formula. If you don't remember all of that, that's perfectly fine. What you do need to remember is what the formula is. So let's look at some examples. And there's kind of, I would say there's maybe 2 or 3 main kind of types of arc length problems that you will encounter. And this first one's probably none of them really. Although the first one's just kind of not terrible. So let's find the length of x equal to y to the 3/2 from the point 0, 0 to the point, what have I got here? 8, 4. All right, so looking at it this way, I have x as a function of y. Could I find y as a function of x? Sure, but they've probably given it to me this way on purpose. So let's say my arc length is going to be the integral from y equals 0 to y equals 4 of the square root of 1 plus dx dy quantity squared dy. Okay, let's take a look. So let's see, dx, and that's why I like to do some of this work on the side. Dx dy, the derivative of x with respect to y is going to be 3/2 x to the 1/2. Sorry, y to the 1/2. Square it, and you get 9/4 y. Okay, that's not terrible. We're doing the integral from 0 to 4 of the square root of 1 plus 9/4 y dy. And that's totally manageable. We can do a u substitution here. We can let u equal the stuff inside the square root. U is 1 plus 9/4 y. And then my du is just going to be 9/4 dy. So 4/9 du equals dy. Great. So this is going to become the integral of the square root of u to the 1/2. And dy is going to be 4/9 du. And then I would encourage you all to change your limits of integration. So if, sorry, here's my u. If y equals 0, u is going to be 1 plus 0. If y equals 4, u is going to be 1 plus 9/4 times 4, which is 1 plus 10. 1 plus 9, which is 10. And then we integrate, we get 4/9 times u to the 3/2 times 2/3 from 1 to 10. So you end up getting, let's see, 8/27 times 10 to the 3/2, which is not a nice number, minus 1 to the 3/2, which is just 1. That's your answer. You could have, if you wanted to, solve for y as a function of x, but I don't think it's really in our best interest. If we solve for y as a function of x, you get y equal to x to the 2/3. The derivative there would be dy dx is 2/3 x to the negative 1/3. And it seems like putting that in, like doing 1 plus that squared, seems like it'd be much, much harder to integrate, right? If I was doing, and I've kind of run out of room here. All right, but if I did have y equal to x to the 2/3 and dy dx is 2/3 x to the negative 1/3. If you try to do the arc length as the square root of 1 plus dy dx squared dx, you would end up with the integral of the square root of 1 plus this thing squared, which is 4/9 x to the negative 2/3. And that's a lot harder to anti-differentiate. Like maybe impossible, maybe not impossible, but certainly more work than a very, very straightforward u substitution. So the thing I want to kind of remind you of here is that, what do I want to remind you? Let me see. Oh, yeah. Is that the variable you decide to use matters a lot. Like sometimes one variable doing one way is literally or virtually impossible, and doing it the other way is super duper easy. So let's kind of, so sometimes they're nice, sometimes they're super funky looking. Like sometimes on your homework, they're going to give you something like the following. What do we got here? Sorry, where'd you go? How do I, sure, let's just do something nice and easy. Like I'm going to say that I want to find the length of f of x equal to, this is always just kind of super funky. Let me make sure I write this the right way. Yeah. Equal to the integral from 0 to x of the square root of, what have I got here? I'm sorry, I have to think for a second just to make something nice. Sure. X squared plus 6x plus 8 dx. It's y squared. Sorry, I need to use a different variable. They like to be extra gnarly about it. Yeah. Sure. Sorry. T squared plus 6t plus 8. Let me just do a quick check to make sure this is going to work. Yeah, that should work out. Okay. So where x is between, let's say x is between, I don't know, 1 and 4. So this is my function. I want to find the length of this from x going from 1 to 4. So I'm just going to throw the formula at it. I'm going to say, okay, here's my formula. Arc length is the integral from, well, they gave me the limits of integration of the square root of 1 plus f prime of x squared. You can use f prime of x or you can use dy dx, right? Same difference. You could also say that that's dy dx if you're calling this y. Okay, can anybody tell me what the derivative of f of x is?
It's x squared plus 6x plus 8.
You're missing the square root. Yeah, the square root, right? Or more generally, right? Fundamental theorem of calculus part 1. The derivative of an integral is just the function inside the integral. So this is exactly going to be the integral from 1 to 4 of the square root of 1 plus, well, the derivative is the square root of, but now it's x instead of t, so it's x squared plus 6x plus 8 squared dx. So the problems on your homework that look like this, where they're giving you some weird looking function that you have to find the arc length of, there was some function that's an integral. The whole idea is that they're actually trying to make your life easy. They're trying to say, oh, look, the thing you're going to differentiate is just going to be the derivative of this integral, which is going to be what's inside it. Then you plop that in there, you square it, you add 1 to it, you're left over with hopefully there's something that's nice, like secant to the 4th. In this case, we're going to be left with x squared plus 6x plus 9, which is x plus 3 quantity squared. Now, I should point out, in this example, it's perfectly fine to just say the square root of x plus 3 squared is x plus 3. So then you do that, you get x squared over 2 plus 3x from 1 to 4. You get some weird numbers, right? Let's say you get a 16 over 2, and not, I mean, they're perfectly fine numbers. You get 8 plus 12 minus 1/2 plus 3. So you get 20 minus 3 is 17, minus 1/2 is 16.5. But I want to mention, I don't really think this is going to come up, but it could, so I feel like I should say something. Let's pretend we have the same exact problem, except now we're saying x is between -6 and -2. Again, this is probably something that you don't have to worry about, but I just want to cover all my bases here. So we get to the same place. We get to the integral from -6 to -2 of the square root of x plus 3 squared. And now here's the thing. I'm going to erase down here if that's okay. I can give you guys a moment if you want. If the insides of a square root is negative, and it is, right? Like if you plug in -6 for x, -6 plus 3 is -3. The square root of -3 squared isn't -3. it's positive 3. So the problem is it's not okay to say that the square root of x plus 3 squared is equal to x plus 3, because it isn't if x plus 3 is negative. So what we actually have to do is say, in this particular case, this is going to end up equaling the integral from negative 6 to negative 2 of negative x plus 3. Technically, what we're really doing is it's the absolute value. Right? The square root of x plus 3 squared is the absolute value of x plus 3. And oh man, I made this even worse than it needed to be. Actually, that's not even right. I actually do really need to use the absolute value. And I'm not going to finish this one because it's terrible. You'd have to then break this up at negative 3. So it would equal the integral from negative 6 to negative 3 of x plus 3 negative plus the integral from negative 3 to negative 2 of, there's a better, you know what, we can do this one if we're smart, of x plus 3. At this point, instead of being foolish about it and writing all this down, what we should instead do is draw a nice picture. You guys know what the opposite value of x plus 3 looks like. And I definitely know what the area under that shape is. That's a triangle whose base and height are both 3. So the area of that is 1/2 base times height. There's a triangle whose base and height are both 1. So the area of that is 9/2 with 1/2, which is 10/2, which is 5. So use the tools you got, right? If you see, now again, I will reiterate. It's probably not something you're going to encounter. It's you could though. Like it's not that far out of bounds. No one's ever going to ask you. Someone totally could ask you this. So just be aware. When you take the square root of something squared, the stuff always has to be positive. Meaning, if you're actually putting in negative things, you have to change them to positive things. Okay.
Wait, James, a quick question.
Yeah.
So, what we calculated, the 5 you calculated, would that be our arc length then?
Yes, the thing we found. So again, right? I did 2 different problems. The first one we did was 16.5 was the arc length when x was between 1 and 4. The second one, positive 5, was the arc length when x is between negative 6 and negative 2.
Oh, okay, yeah. Makes sense.
2 different problems I was doing.
Mm-hmm.
Just a little bit. No, I guess it's not. A little. I'm mildly surprised that this one's bigger than that one. Yeah, I'm a little surprised. Oh no, I'm not. No, I take it back. I'm totally not surprised. Never mind. Okay. So these types where you're given your function is just some integral of some probably square root of something is usually not terrible at all. Trying to think if there's another good one that we could do. It's not just bonkers. Sure, I'm going to pull this one from the book that feels dangerous, but I'm going to try it anyway. Let's say we have x equal to the integral from 0 to y of the square root of cosine of 2t dt from y is between 0 and pi over 4. So again, we want to find the length of, the arc length or the length of this function of y, right? This is a function of y. So just so you guys are clear, right? Whatever variable is up, right, in your limits of integration, that is the variable that we are a function of. So when they write x equals integral from 0 to y, oh, x is a function of y. If they write y equals an integral from 0 to x, oh, y is a function of x. So let's throw it at the formula. Let's throw the formula at it. So the length here is going to be the integral from 0 to pi over 4 right? These are y values, so we should have a dy of the square root of 1 plus f prime of y squared. Okay, everybody should be able to tell me really, really easily. I'm worried. I'm already worried about my like, uh-oh. Sometimes we make mistakes. What is f prime of y, everybody?
Square root of cosine of 2y.
Excellent. So then that's what's going to go here. So we're going to get, except it's going to be, I know what this trick is, right? Because the square root is squared. And you might look at that, and I wouldn't blame you for being like, well, that doesn't look nice at all, James. What's your problem? Well, it is actually not that terrible. There's a formula for this. And the formula is the following. So here's the formula I would actually encourage you to know. You guys know the, how do I want to say it? Let's go, sorry, I'm trying to think of the right way it says. Let's go this way. So there's a formula for cosine of 2 theta. There's a few formulas for cosine 2 theta, actually. It's, the one I remember is cosine squared theta minus sine squared theta. And so what I'm going to do is I'm going to replace the sine squared with, I'm going to use this other trig identity, sine squared theta plus cosine squared theta equal to 1, and say that sine squared theta is equal to 1 minus cosine squared theta. So then cosine of 2 theta equals cosine squared theta minus 1 minus cosine squared theta. So simplifying, cosine of 2 theta equals cosine squared plus cosine squared is 2 cosine squared theta minus 1. Add 1 over here. So 1 plus cosine of 2 theta equals 2 cosine squared theta. 1 plus cosine of 2y equals 2 cosine squared of y. How about that? So I will, again, reiterate, this is kind of tricky, right? Like, I definitely remember the first time I saw this, I was like, what do you do with that? Oh, you use this half angle identity garbage? Oh, okay. But that is what you do. Yeah. You could also, if you wanted to, you could actually start by just plugging this in for it. You'd be like, oh, that's 1 plus cosine squared minus sine squared, but then 1 minus sine squared is cosine squared. So you get cosine squared plus cosine squared, which is 2 cosine squared. Either way.
It says sine squared theta. It says plus, right in the bottom right here. Sine squared theta. What is that? Sine squared theta plus.
So sine squared theta plus cosine squared theta equals 1. And I know it does not look excellent. And this is just your everyone's favorite trig identity.
Okay. Thank you.
So then this is equal to the integral from 0 to pi over 4 of the square root of 2 times the square root of cosine squared. And I don't need an absolute value here because cosine is positive from 0 to pi over 4. So then the antiderivative of cosine is sine from 0 to pi over 4. So I get the square root of 2 times sine of pi over 4 minus sine of 0. Sine of pi over 4 is root 2 over 2. Sine of 0 is 0. So you end up with root 2 times root 2 over 2, which is just 2 over 2, which is 1. It's kind of a neat answer, right? That the length of this bizarre looking thing from 0 to pi over 4 is in fact 1. Okay, so these ones, obviously you'll encounter a bit. There's been at least a couple of them on your homework, but let's kind of roll around to the last, and what in my opinion is the kind of last type of arc length problem you are likely to see.
James,
Yes.
I have a good question. So when we have like our L equals integral of 0 to pi over 4 square root of 1 plus cosine 2y dy, and when we square that, what would that be? Wouldn't it be like
When I square what?
just the our f prime of y?
So f prime of y was the square root of cosine of 2y.
Oh yeah, huh? Then we just since we squared it, yeah, makes sense. Thank you, James.
So a lot of these arc length ones where the function is some integral, it's usually an integral of a square root of a thing. So that when you differentiate it, you just get the derivative is the square root of that thing. And then when you square it in the formula, you just get the thing. So there's one other type that they talked to a couple of you about earlier today in office hours. And this comes up all the time. So I'm going to try and be very, very methodical about this. Let's look at this example. Let's say I want to find the arc length of this function of y equal to x to the fourth. Do I really want to do this one? Yeah, that's fine. X to the fourth over 4 plus 1 over 8x squared. So, and x is between 1 and 2. So here's what I will say. If you have a function that looks like some power of x plus some other power of x, or some power of y plus some other power of y, usually this process that we're about to encounter is what always is going to happen. And I will tell you right now, looking at this function, I already know the answer to this integral. I know the answer to this integral, not because I'm looking at the answers, because I've seen these a million times. I know my answer is going to be the following. The answer is going to be x to the fourth over 4 minus 1 over 8x squared, evaluated between 1 and 2. Now, that doesn't mean you don't have to show the work, but the nice thing to know is that if you recognize this kind of thing, you can be pretty sure that the final answer is going to be the same function, except the middle sign is flipped and evaluated at your points. Okay, all right, just one second, I'm getting where it's probably not an important call, but I should take a look at it just to be sure. It does not look important. Yep, just a bunch of garbage phone calls. Okay. Yeah, all right, so, no, actually, wait, there's one thing about that. That was okay, that was the other day. All right, so, here's what's gonna happen every time. In fact, let's just, so I'm gonna like, I would rather do the derivative and the squaring kind of one thing. So I know eventually I'm gonna do the integral of the square root of 1 plus dy dx quantity squared from 1 to 2. That's what I'm going to work on. So what's going to happen is we're going to take the derivative. So dy dx is equal to the derivative that's going to be 4x cubed over 4. And this is 1/8 times x to the negative second. The derivative of that is going to be minus 2/8 x to the negative third. A good thing to kind of recognize, or a good indicator that what's going to happen is about to happen, is that after you differentiate, the signs of the variable are the opposite powers. One is positive something, one is the same negative something. Okay. So let's simplify this just a tiny bit. That's x cubed minus 1/4 x to the negative third. Now let's square it out. So this is going to be dy dx squared. X cubed minus 1/4 x to the negative third squared. So when you multiply, when you square something out like this, it's always the first term squared plus 2 times the first term times the second term plus the second term squared, which is going to be 1/16 x to the negative 6. All right, so check this out. When you simplify this middle term here, the x to the third times x to the negative third becomes x to the 0th, which is just 1. So these kind of cancel each other out. And 2 times negative 1/4 is negative 1/2. And that is kind of the big deal, is you are always expecting the middle term to be nothing else other than -1/2 every single freaking time. Okay, here's why that's important. What are we going to do to dy dx squared? We're going to add 1 to it. So if I add 1 plus dy dx squared is going to equal the same thing, but now the sign here changes. Right? It's x to the 6th plus 1/2 plus 1/16 x to the -6th. All right, now here's the really key observation. This is going to factor. And this is going to factor exactly as this, except the middle sign is going to be the opposite of what it was. So this is going to factor as x cubed plus 1/4 x to the -3rd quantity squared. Hopefully you guys can see that. Right? If I square this out, I'm going to get x cubed squared, which is x to the 6th. I'm going to get 2 times this, which is exactly the same as 2 times this, except I don't have the negative anymore. So it's going to be a positive 1/2. And then I'm going to get this square, which is 1/16 x to the -6th. Oh, look. It's super duper easy once you see the pattern. So then to actually calculate the arc length, and of course I've run out of room on this side of the board, I guess I can go over here. My arc length, well, that's just going to be the integral from 1 to 2 of the square root of x cubed plus 1/4 x to the -3rd squared. But the square root of that thing squared is just x cubed plus 1/4 x to the -3rd. Which is equal to the integral from 1 to 2 of x to the 3rd plus 1/4 x to the -3rd. And if we integrate that, we get x to the 4th over 4 plus 1/4 x to the -2nd over -2, which is going to be 1 minus 1 over 8x squared. Just like we predicted. So here's kind of the great and terrible thing about these problems. The great thing is you know what the answer is supposed to look like. If you see something like this, you're like, great, switch the sign. That's my final answer, evaluate between 1 and 2. The terrible thing is you still need to show all this work to get to the place you already know how to get to. But you do need to show the work. So finishing this one off, plugging in 2, we get 16 over 4 minus 1 over 8 times 4 minus, plugging in 1, 1/4 minus 1/8. And that's something. Let's see, I've got 4 minus 1/32, and 1/4 minus 1/8 is 2/8 minus 1/8, which is 1/8. So that's, let's see, I don't know, 4 minus 1/32 minus 4/32 minus 5/32, something like that. 128 minus 5 is 123/32. Great. There's a lot of problems like this. Let's do at least one more, maybe 2, maybe 3, maybe 4. No, 4 is not one. So let's look at another one. But I really want to stress, with problems that look like that, you're looking to see that you get a -1/2 after you square the derivative. So that when you add 1, then you've got the opposite sign and it factors back out essentially the same way. So let's look at this example. Let's look at, let's say we've got y equal to x squared minus the natural log of x divided by 8. And then we're going to again say x is between 1 and 2. All right, so I'm just going to go full formula. Integral from 1 to 2 of the square root of 1 plus the derivative of that. So the derivative of that is 2x minus derivative of the natural log of x over 8 is 1 over 8 times 1 over x. All right. I think I put this in. That's here. So multiplying this out. So 2x minus 1 over 8x squared is going to be 4x squared. The middle term should be negative 1/2, but let's check. Middle term is 2 times 2x times negative 1 over 8. Right? It's always, right? There's this formula I'm using that you should, my hair is like really in my face. There's this formula you guys should be aware of. That a plus b squared is a squared plus 2ab plus b squared. That's what I'm using here. This is a is 2x, and b is negative 1/8 1 times 1 over x. So it's a squared plus 2 times a, which is 2x, times b, which is negative 1 over 8x. And then, not gonna fit, plus negative 1 over 8x squared. Sorry, that's terrible. I want to make it fit. So here's what we've got. I'm going to write it again. We've got the integral from 1 to 2 of the square root of 1 plus 4x squared. 2 times 2x is 4x. 4x over 8x. The 4s and 8 cancel. You go 2 in the bottom. The x's cancel. You get a negative 1/2. Plus negative 1 over 8x squared is 1 over 64x squared. And we know how this, right? We know that this part in parentheses, and that is your 2x minus 1 over 8x quantity squared. Then we go to the next step where we add the 1. I can fit this in this time. This is going to be the square root of 4x squared plus 1/2 plus 1 over 64x squared. And again, I don't think it's too much of a leap to say, oh, look, that has to be 2x plus 1 over 8x squared. Right? If you square out a binomial and then you change the sign of the middle, you're just changing the sign of the middle that was connected in. Then the rest, oh, don't forget your dx's, they're super important. So then we get the integral from 1 to 2 of 2x plus 1 over 8x dx, right? The square root of this squared is just that. And then that's going to be x squared. The integral of 1/8 times 1 over x is 1/8. The integral of 1 over x is the natural log of the absolute value of x from 1 to 2. And look, I'm back at the function I started with, except the sign between the two pieces is changed. So then you're going to get 2 squared plus 1/8 natural log of 2 minus 1 squared plus 1/8 natural log of 1. Natural log of 1 is 0. 4 minus 1 is 3. So you get 3 minus 1/8 natural log of 2. Neat. Questions about this?
Oh, yeah, James, I have a quick question. So from our last line of that you wrote, like the integral of 1 to 2 of 2x plus 1 over 8x dx, we just anti-differentiate, right?
Yeah. I'm just from here to here, I'm just anti-differentiating.
Okay, yeah. Yeah, I just wanted to make sure because sometimes I zone out and I forget what we.
Yeah, no problem.
Thank you, James.
You're welcome. Other questions?
You said the answer was 3 minus 1/8 natural log of 2?
Oh, it should be plus. Yeah.
Okay.
Right, it's 4 plus 1/8 natural log of 2 minus 1. So 3 plus. Good eye there.
Okay.
I was testing you. Not really. Okay, so what I really should do, so should I do another example of this, or are we set for this? Another example? If not, I think we should move on to arc length. I mean, sorry, that's what we're talking about. I meant surface area. All right. Nobody said anything. I'm going to move on to surface area. Surface area can be a big pain in the butt. But it doesn't have to be. So I want to find, here's what I said. I want to find the surface area of the quote unquote bowl formed when the curve y equals x squared, where x is between 0 and 2, is revolved around the y-axis. All right, so let's draw this thing. I'm going to try and draw it. I'm going to try and do a good job drawing it. I mean, I always try and do an okay job. I'm going to try and do a really good job. Okay, so great, there's our bowl. I don't want to do that actually. Right, so I'm thinking of this as literally being like a bowl, right? Like there's some, it's empty inside, right? It's not a solid because we didn't take the region and revolved it. We took the arc length or the arc and revolved it around. So you just take this arc and revolve it around, you're just getting the surface of the solid that you would have gotten if you revolved the region. And the idea is, just like every other time we've been doing stuff, we're gonna add up a small slice of the thing using an integral. So, right, before our slices have been rectangles, or our slices have been discs or washers or cylindrical shells. Now our slices are going to be slices of this surface. So it's gonna look like, well, here's a slice of my surface. I think of it as looking like a rubber band. I feel like that picture is not the best. Let me draw it again. Okay, well. That's I'm messing it up. No. I want to make it look kind of exaggerated this way, so you can kind of see. Right. Rubber band. I can go get one if you want, but I think everybody has seen a rubber band in their life, hopefully. So I want to find the area of this rubber band. Well, if I straighten it out, right, if I like cut it right there and straighten it out, it kind of looks like this. Where the length of the rubber band is just the circumference of the surface. So just like with the shell method, actually, I'm going to, how do I want to say this? Yeah, I'm not going to say that. I'm going to say this. I'm going to say the length of this is just 2 pi times the radius, right? So my radius is, this way. the radius. And how wide is the rubber band? And this is a question that's not maybe super clear. Well, right, if I'm a little bit more, right, the rubber band, and this is where it actually is important, right? The top circumference is definitely more than the bottom circumference, right? It gets bigger as it goes out. And the problem here is that, right, there really is a significant change. It's not something, right, no matter how kind of small you make your rubber band, it's still kind of slanting outwards. This length here, right, isn't just a change in X or a change in Y. It's a change in the length, a ds, if you will. So the surface area of this band is 2 pi r times ds. Okay, this is where things get extra complicated. I want to do this in terms of x. Great. So for this band here, the radius, well, in terms of x, I've gone out x. Okay. So the volume of my band, the area of my band is going to be 2 pi times x times the square root. That's not enough room, James. Let's be realistic. Sorry. The surface area of my band is going to be 2 pi times my radius x times the square root of, well, right, times ds, which is the square root of 1 plus dy dx. So dy dx is just 2x quantity squared. Let's calculate it. Oh, sorry, so now we want to find the integral. The integral is going to be the integral of this from x equals 0 to x equals 2. So the surface area of that shape is going to be the integral from 0 to 2. What was it? 2 pi x times the square root of 1 plus 4x squared. Questions about what we've done before we move on?
Yeah, James, I just wanted to ask you if you could flip the board really like really quick. Okay, so 2 pi x. Okay,
So,
thank you.
the thing I would encourage everyone to remember, just like just like for for disk method, we find the volume of the volume of a disk is pi times for washer method, the volume of your washer is pi times the big radius squared minus pi times the little radius squared, all times dx or dy. For the shell method, it's 2 pi r h times d whatever. For surface area, it's always 2 pi r ds, where r is the distance to your axis of rotation, and ds is the usual square root of 1 plus the derivative squared. Which derivative? Whatever one makes sense, depending on which variable you're trying to use. Okay, so I'm going to do a u sub here. I'm going to let u equal 1 plus 4x squared. Du is going to be 8x dx. 1/8 du is x dx. So this integral is going to become the integral, let's see, I've got a 2 pi. My x dx is going to be a 1/8 du. And then I've got the square root of u. And I'm going to change my limits of integration. So I'm going to say if x is 0, u is 1 plus 4 times 0 squared. If x is 2, u is 1 plus 4 times 2 squared, which is 4 times 4 is 16 plus 1 is 17. Not the nicest number ever. Oh well. So then we do this, we get pi over 4. Integral of u to the 1/2 is 2/3 u to the 3/2 from 1 to 17. So that's going to be what? Pi over 6 times 17 to the 3/2 minus 1. Okay, now I'm gonna let me take a quick look at this before I get too crazy here. Sorry, I know you want. Let me see here. That should work out. Okay. So, questions about this before we do the same problem a different way?
Yeah, yes, James, I have a quick question. So when we do 1/8 du equals x dx, where does the x go once you do like?
Well, so the x dx.
Oh, it cancels out with the one in front. Huh?
Replaced by the 1/8 du.
Mm-hmm.
That's it.
Okay, that makes sense. Thank you, James.
All right, so now here's the thing. And this is kind of the part that kind of blows people's minds a little bit. For surface area problems, you can almost always do it using either variable. Meaning you could take this same region revolved around this, same arc, right? It's not a region, it's an arc. This arc here revolved around the x-axis, the y-axis, holy geez. And use, instead of the y as a function of x, you could do x as a function of y. So I'm going to do that, and I'm going to show you guys the kind of key difference here. Well, that's kind of a different colored pen. So instead of y equal to x squared, we're going to say, well, now our function is x equal to the square root of y. And it is the positive square root. That pen does not look like it's showing up very well at all. It is x equal to the positive square root of y, because we're on the right side. And if x goes from 0 to 2, y is going to go from 0 squared to 2 squared, which is 0 to 4. The formula is still the same, but it's different. So the surface area is still 2 pi r ds. But now we're doing things in terms of y. So I'm going to leave the radius off for a second. The ds, now instead of being the square root of 1 plus dy dx squared, right, like it was before, now our ds is going to be the square root of 1 plus dx dy squared, right, because we're doing things in terms of y. So if x is the square root of y, which is y to the 1/2, dx dy is just 1/2 y to the negative 1/2. Or I usually prefer to write it as 1 over 2 times the square root of y. Any questions about that? And yeah, this is the surface area of my rubber band, right? Because we have to then integrate it to get the total surface area. Okay, so this next question isn't meant to be a trick, but it might be hard for you to see what the answer is. When we did things, so the radius of this rubber band, when we were doing it in terms of x, the radius was x, right? It's a distance from here to there. What's the radius now? Did it change? Is my rubber band different?
No.
No, rubber band is still the same. Is the radius still x?
No.
Well, I mean, yes and no, right? Yes, it's still x in that it's still the same thing, but we can't use x because we're in terms of y. Mm-hmm. So what is x equal to in terms of y?
Would it be just y? Oh, I see.
So here's the deal. When you're doing these surface area equations, you're always going to be 2 pi r ds. And so let me just talk in terms of this particular problem. If you're doing it in terms of x and you're going around the y-axis, your radius is just x. If you're doing it in terms of y and you're going around the y-axis, your radius is x equal to the function of y. So let me write this on the other side. I don't want to. write it after we finish this problem. So we're going to do this to see that it's actually the same. So I'm going to now integrate from 0 to 4 of 2 pi times the square root of y times the square root of, what was it? 1 plus, I'm going to write that as 1 over 4y. Right, because it's 1 over 2 root y quantity squared. And now here's the great thing. When you have square roots multiplied together, you can multiply them together. And this is totally 2 pi integral from 0 to 4 of the square root of y times 1 plus 1 over 4y, which is just y plus 1/4. Do a u sub. I'm going to let u equal y plus 1/4. Du is going to equal dy. So this is going to be the integral of u to the 1/2 du. And I'm going to change my limits of integration again. If y equals 0, u is going to be 1/4. And if y equals 4, u is going to be 4 plus 1/4, which is 17/4. So looking good, I'm getting a 17, which I got a 17 here. So then integrating this, we get 2 pi times 2/3 u to the 3/2 from 1/4 to 17/4. And plugging that in, 2 pi times 2 over 3 is 4 pi over 3 times 17/4 to the 3/2 minus 1/4 to the 3/2. Okay, and now these are actually the same, because what happens here is 17 to the 3/2 over 4 to the 3/2 is 17 to the 3/2 over 8. This is 1 to the 3/2 over 8. So this is really, sorry, I'm running out of room, I know. This is 4 pi over 3 times 17 to the 3/2 minus 1 all over 8. Because 4 to the 3/2 is 8. But if you bring that 8 out, 4 pi over 3 times 8 is 4 pi over 24, which is pi over 6. Same. Okay, I know that might be kind of a lot. Here's what I want to say. There are kind of there's actually really 4 different formulas for surface area, which is kind of a giant pain in the ass. Let me show them to you real quick. So let's say we have this thing here. Right, here's our arc length, and you can either think of it as y equals a function of x, or as x equal to a function of y. Cool. Let's say we're going around the y-axis. So surface area around the y-axis. Okay, well, around the y-axis, my radius is x. So my surface area is either going to be, in terms of x, the integral of 2 pi x times the square root of 1 plus f prime of x squared dx. From I don't care to I don't care where, right? If you want to call this, I mean, this looks like 0, 0, right? To a comma b. And this would be from 0 to a. Or the surface area could be the integral from y equals 0 to y equals b of 2 pi times the radius. Well, now the radius in terms of y, the radius is still x, but x is equal to a function of y. And then the arc length ds is 1 plus your function's derivative squared dy. Or if we go around the x-axis, then our radius is equal to y, because the distance from the axis of rotation is how high we are, which is y. So that's going to be then So if we're going around the x-axis, it's either going to be the integral. So let's see. In terms of y, it's going to be 2 pi times the radius, which is y, times the square root of 1 plus. So we're doing things in terms of the function y. So it's going to be g prime of y. Excuse me, dy. And then y would go from 0 to b. Or it would be the integral from 0 to a. It'd be 2 pi times not x, but the radius in terms of x. The radius is y. Y equals f of x times the square root of 1 plus f prime of x squared dx. Oh, that should be squared, sorry. So there's really one formula, right? The formula is you're going to integrate for surface area. It's the integral of 2 pi r ds, but the r depends both on what variable you're using and which axis you're rotating around. So if you're using x and you're rotating around the y-axis, great, your radius is x. If you're using y and you're rotating around the y-axis, great, your radius is x as a function of y. So what I would really, really strongly encourage everyone to think about for these surface area ones is that your radius is always just the variable. If you're going around the y-axis, your radius is just x. If you're going around the x-axis, your radius is just y. But if you're using the other variable, then you have to say, oh, well, what does that equal in terms of the other variable? Then it's not just the other variable, it's whatever the function of the other variable is. Whew. Kind of weird. That said, let's talk about revolving that first region now around the x-axis. And so this is where really most of the time you'll kind of always have a choice of which way you want to do it, which is not always a great thing, right? Sometimes it's better not to have choices. You're like, okay, I'm just going to do it the only way I can do it. So let's revolve. Again, here's our arc. Y equals x squared around the x-axis. So now I've got this kind of shape. Right? And I want to find the surface area of that. So the surface area, so again, I like to think about what's the surface area of my rubber band. Well, the surface area of my rubber band is, and I didn't really drop very well here. And surface area of my rubber band is 2 pi times the radius times the ds. If I kind of can pick between one or the other, I usually like to keep my radius as just being whatever the variable is, right? So let me ask you guys here. Would the radius be y or would the radius be x? If I'm going around the x-axis. Question, I would like an answer. You guys can just guess. Totally, right? The radius is y. Right, if you're measuring to the x-axis, you're saying, how high am I? Oh, how high is y? How many times can I rhyme with y? I don't know, probably not that many more. Okay, so the radius is y. Or if we wanted to, it could also be x squared. Each of those would be a perfectly fine choice for the radius. It just depends on how we want to do it. Well, let's do it in terms of y. So then my surface area of my band is going to be 2 pi times y times ds, which is going to be the square root of 1 plus dx dy squared. Or, you know, what x is a function of y. So x equals the square root of y, and the derivative of that is 1 over 2 root y squared. So I might, oh, and of course, don't forget the dy. this might not be the best choice. Or it might be that this problem actually can't be done, right? Because I'm looking at the other way of doing it. It's also terrible. So I don't think we have the tools to do that yet. That's okay. So then the surface area total would be the integral of 2 pi times y times the square root of 1 plus 1 over 4y. Yeah, I don't think we know how to do that yet. It's okay. Yeah, it's fun. It's all right. Some integrals we don't know how to do. So what time is it? 3:42. Let me give you guys 1 or 2 more, and then we'll call it a day. So let's say, so again, just like before, when you're revolving stuff, you typically have choices, but you're limited by your ability to solve for one thing as a function of the other thing. So for example, if I was given, say, y equal to the square root of 2x minus x squared, where x is between 0 and 2, and I'm revolving around the x-axis, I don't have much of a choice. It's not impossible, right? You could solve this for x as a function of y. It's not nice though. Typically, if they're giving you the function one way and it's relatively complex, you usually want to stay that way. So I'm going around. So this looks, I don't know, this looks something like if x is 0, you get 0. If x is 2, you also get 0. If x is 1, you get 1. This looks kind of, I don't know, like that. It's not a half a circle, but I don't really know exactly what it looks like. That's okay. So then, right, we want to rotate this around. So we're getting the surface area of this shape here. So the surface area of my band is going to be 2 pi r ds. The radius, just like in the previous problem, the radius is y. But I don't want to do things in terms of y, right? Because I don't want to write x as a function of y. So I'm going to say, oh, my radius, I'm going to sub in. I'm going to call an audible and say the radius is instead what y is equal to, which is the square root of 2x squared. So then my ds is the square root of 1 plus the derivative of this square. Dude, let's take a moment here. Y prime is going to be, that's that to the 1/2, so y prime is going to be 1/2 times that. So the negative 1/2 times the derivative. It's looking terrible. Don't worry, it's going to work out all right. Times, let's see, the derivative of this is 2 minus 2x. Whew. We're going to square that. Let's do a little bit of simplifying before I square that. So this is equal to, I can factor out a 2 here. So I've got 2 over, oh, those cancel, times 1 minus x over the square root of 2x minus x squared. Hopefully everyone's okay with that. And so then squaring that, I'm going to get 1 minus x squared over 2x minus x squared. Right, I squared the top, I squared the bottom. So now the surface area is 2 pi times this times this. So my volume, my total volume, is the integral from 0 to 2 of the square root of 2x minus x squared times the square root of 1 plus 1 minus x squared over 2x minus x squared. And the important thing to remember is that square roots you can multiply together. So if you multiply this times this, you're just going to get 2x minus x squared times the inside, which is actually going to work out really nice. I forgot my 2 pi. Don't want to forget 2 pi's, let alone 1. So I should put on that side of it. So 2x minus x squared times 1 is going to be 2x minus x squared. And 2x minus x squared times 1 minus x quantity squared over 2x minus x squared. The 2x minus x squareds cancel out, and you get 1 minus x squared, which is 1 minus 2x plus x squared. I can say more about that if anyone would like me to. Interesting. So I have a work chat open. I just saw someone posted a link to the LA Times about how the University of California and Cal State schools will require the COVID-19 vaccine. There's probably more information about that in the fall, but definitely something to look into if you're planning on attending in person in fall, which I don't know if that's required or not, but definitely keep sorry to change gears so quickly, but just something to be aware of, right? Make sure you are paying attention to the news from the University of California about what they are requiring of you for fall quarter, because it sounds like there's going to be a lot of in-person class in fall quarter. Sorry, back to the math. So just to want to make sure everyone's cool with this, right? We did this, distributed to this, and to that. And it's perfectly fine since they're all in the square root. But now look, minus x squared and x squared cancel. Wow, this worked out really nice. 2x and minus 2x cancel, and you get the integral from 0 to 2 of just 2 pi, which is just 2 pi times 2. So you could like say, okay, it's 2 pi x from 0 to 2, which is 2 pi times 2 minus 2 pi times 0. Or you could just say, when you integrate a constant, it's just the constant times the length of the integral. That was a pretty cool problem. Worked out very nice. That said, when you see something, right, in the beginning, this looked like it wasn't going to be very nice. They look pretty gross. But don't let that discourage you. A lot of these surface area problems start off kind of gnarly, but they work out pretty well. I will also mention, for these surface area problems, you will see surface area problems that have the look of those -1/2 problems we were talking about earlier. Let's do one last example, and then I will call it a day. Let's say I want to find the surface area of this. X equal to, and I need to be careful here, y cubed over 6 plus, I need to be extra careful here. That should work out fine. 1 over 2y, where y is between 2 and 3. And let me think for just 1 second. Shouldn't actually matter which way we do it. Well, let's go around the x-axis. First observation. There's no way we're solving this for y as a function of x. So if we're going around the x-axis, I don't know what this looks like from 2 to 3. If you plug in 2 for y, you get, I don't know, you get something. You plug in 3, you get something else. Or maybe it looks like that, maybe not. I mean, we've got some sort of funky looking surface there. Okay, I want to find the surface area of that surface. So I'm going to do, the surface area is equal to the integral from 2 to 3 of 2 pi times my radius times my ds. But I have to be in terms of y. So my ds has to be the square root of 1 plus dx dy squared y. And let me ask everybody. I already see people written the answer from before. If I'm going around the x-axis, what does my radius have to be? Oh yeah, it has to be y. And since we're in terms of y, we're going to leave it as is.
Wait, James, could you repeat that once more?
Yes. So surface area is the integral of 2 pi r times ds. And since we're going around the x-axis, right? In fact, let me draw, right? We're looking at our rubber band, which I've drawn poorly here. Sorry. There's our rubber band, and the radius of that circle in the rubber band, that radius, that's y. So then the surface area is 2 pi times the radius y times ds, which is always the square root of 1 plus whichever derivative makes sense. Okay, so we have enough time? We have enough time, yeah. So then here's what's going to happen. So let's do the derivative off the side. I'm going to do it kind of fast. So dx dy. So this is y cubed over 6 plus 1 over 2 y to the negative first, if you prefer. The derivative is going to be 3x squared over 6, sorry, 3y squared over 6 minus 1/2 y to the negative second. Or simplifying a bit, y squared over 2 minus 1 over 2y squared. When we square that, dx dy squared is going to be first thing squared, which is y to the 4th over 4, 2 times the first times the second thing. So let's see. This times this is going to be y squared over 2 times negative 1 over 2y squared is going to be the y squared to cancel. It's going to be negative 1/4. And then 2 times that is going to be, oh, big surprise, negative 1/2. And then we're going to add that square, which is 1 over 4y squared. So then if we add 1, I'm just going to jump straight to kind of the conclusion here. 1 plus dx dy squared is going to be this with a positive 1/2, which is then going to be this squared, but with a positive sign in the middle. So it's going to be y squared over 2 plus 1 over 2y squared. Okay. And then that's what's going to go inside here. So this is going to equal the integral from 2 to 3 of 2 pi times y times the square root of this, which is y squared over 2 plus 1 over 2y squared. So then you have to multiply it out. So Racing keeps wanting to throw itself on the floor here. So multiplying it out, you get 2 pi integral from 2 to 3 of y times y squared over 2 is y cubed over 2. And y times 1 over 2 y squared is 1/2 times 1 over y. And then we integrate this. So we get 2 pi integral of y cubed over 2 is y to the 4th over 4 times 2 is 8. This is going to be 1/2 natural log of the absolute value of y. 2 to 3. And then we can plug in and get some final answer, which is going to be 2 pi times a bunch of garbage. 3 to the 4th is 81 over 8 plus 1/2 natural log of 3 minus plug in 2. 16 over 8 is 2 and 1/2. So there's the terrible surface area of this particular function.